Okay, so it's Monday. So what I would like to do today is to start off where we left off last week, which was discussing isotopes. And then we will go through a discussion of the periodic table today. Okay, so let's start reminding ourselves a little bit about isotopes. Okay, so this is you see this term quite a bit in chemistry. All right. The idea is the following. If you have a particular element, so I'm going to draw one of the little squares from the periodic table, and I'm going to pick, let's pick carbon. Carbon's the easiest one for me to remember. There we go. Okay. What you'll see, so this is carbon, is that there are two numbers listed for each element. And the number at the top, it doesn't have to be drawn in the center. Sometimes people shift it off to the left, but it's usually above the symbol. This is the atomic number. We talked about that last week. The atomic number is the number of protons in one atom of this element. Okay, so that means that carbon has 6 protons in one atom. Each atom of carbon has 6 protons. That's a number that cannot change for a particular element. So if that number were 7, it wouldn't be carbon anymore, it would be nitrogen. If it were 8, it would be oxygen. If it were 92, it would be uranium. So that number up at the top is called the atomic number. Let's remind ourselves how this works, right? You've got this nucleus, which is, I'm going to draw this little circle, so that's your nucleus. And inside that nucleus, there are these protons. So if it's carbon, that means there's 6 protons in the nucleus. And then outside of that are where the electrons are. Now, technically, this is a incorrect model of the atom, but we know more about the atom now than when this kind of nuclear model was proposed, or planetary model. But for now, let's just assume that the electrons are outside the nucleus. And as you go through chemistry, you'll learn more and more sophisticated ways to think about this. But remember, for an atom, the number of electrons is equal to the number of protons. So if you have 6 protons, you also have to have 6 electrons, right? And they're on the outside. And then there are also these other particles in the nucleus, right? So I'm going to try to draw them in there. And those are the neutrons. And roughly speaking, the number of neutrons is close to the number of protons in an atom. So sometimes it's a little more neutrons. Sometimes it's the same, could be the same number of neutrons as protons. They could be equal to each other, but there is no hard, fast rule that they have to be equal to each other like we have with the electron and the proton. The protons and electrons have to equal each other because they have opposite electrical charges. So if you have 6 positive charges, you've also got to have 6 negative charges, but that's not true for the neutron. Roughly speaking, the number of neutrons is pretty close to that of the protons. So if you have 6 protons, there's a good chance you got 6 neutrons, but you might have 7, and you might even have 8. They don't have to be equal to each other. Okay, so that's the atomic number. That's the number of protons. Now, sometimes this can be confusing. Sometimes you'll see it written this way. Now that's a little confusing because now we're writing the 6 below the carbon. It's actually not below it, it's just a little bit offset and to the left. But again, that's just a different way of writing it. There are different notations that are used. So again, this is the atomic number. And again, so that's the number of protons, right? So it can either be in the periodic table, it's written above. If it's not in the periodic table, it's often written below or to the left, I should say. Okay? Subscript is subscripted on the left. Now, there's another number, and this can be kind of confusing. So the other number is up here. And that is not going to appear in the periodic table. So you won't see this number in the periodic table, but you will see it in notation like this, or you might see it like this, or you might see it like this. So it could either be written with the number up above to the left, a superscript to the left, or it could be written as the symbol of the element with that same number, 12, or the name, the full name of the element, and then a hyphen, just like we had over here, and then that number. That number there is not the same number as this one. It's not the same as this one. They're close, though. This is called the mass number. Okay, the mass number. And roughly speaking, the mass number is close to the same as this number over here. They're pretty close. One way you can tell the difference is the mass number is going to be a whole number. It's going to be an integer value. 1, 2, 3, 4, 92, 200. It's going to be whole numbers. The number here, which we'll talk about later, we do that in this chapter, this number is going to be a decimal number. It's going to have point something, 12.0, 238.2. It's going to have a decimal number. So that tells you right there they're different. Okay. But sometimes they're pretty close to each other. So the mass number, okay, I already told you what the atomic number is. The mass number, very simple. It's the number of protons plus the number of neutrons. It's just the two of them added together. So it's telling you the total number of particles that are in the nucleus. So it's not electrons, just protons and neutrons. That's called the mass number. So if I said, hey, the mass number equals 13, you would know right there that your protons plus neutrons equals 13. You would know the total number of protons and neutrons. And the term that we use for those particles is we call them nucleons. Nucleons are just the particles that are in the nucleus. So that'd be protons and neutrons. Okay. So 13 would be the mass number for that. That just means you got 13 together. So here's the way we deal with this. What we do is we say often it's useful to give people or to communicate to people the mass number, but not the atomic number. So you might see something like this. You might see C13. And so that number right there tells you, okay, let's write it out. Mass number equals 13, which means the protons plus neutrons equals 13. That's the number of nucleons, right? So then you say, okay, well, I know the total number, but what about each one? How much is the protons? How much is the neutrons? That's when you go to the periodic table. Just go back to the periodic table. Okay, so if they give you this, I don't want to put a square around there because you might think that's the periodic table. If they give you this, C13, you just go to the periodic table, you look up that symbol, you look up carbon. Very simple. Oops, sorry, 1 second. You look up that number. In fact, let me do this as long as we're doing this. Let me bring up a periodic table. There we go. And let's share this so you can see it. You bring up the periodic table and you just look for carbon. You look for C for carbon. So if you look at this one, actually, it's interesting. You can see that the carbon, they offset the atomic number to the left. So it's just a style. It's just a stylistic thing. They put the 6 off to the left. I prefer to have it in the middle. I don't know why some people do that, but they put the 6 off to the left. So that's the atomic number. That's the number of protons. So the mass number is not going to appear in this table. What will appear is the atomic number. Okay, so let me stop sharing. And then let's bring this back up. Let's see if this works again. Okay, there we go. So protons plus neutrons equals 13. Again, that's your mass number. And then you say, okay, well, on the periodic table, there's a 6. That's your atomic number. That's equal to 6. So now essentially what you know is you have 6 protons, right? Sometimes we put a little positive next to it just to say it's positively charged. Okay, so you get 6 protons. And so the protons plus the neutrons equals 13. So how do you find the number of neutrons? You just subtract. N would be 13 minus the number of protons, which would be 13 minus 6. You got 7. So right now we know that this particular form of carbon has 6 protons. It has to have 6 protons because it's carbon, but it also has 7 neutrons. How many electrons? 6, right? It's got to have 6 electrons because the number of electrons is equal to the number of protons. And this is called carbon-13. And that is an isotope of carbon. It's an isotope of carbon. So there are other isotopes of carbon. Let me show you some of them. There's carbon-12. Okay, well, the mass number would be 12. So we've got 12 protons plus neutrons, right? So we know we have 6 protons because it's carbon. That's what we get from the periodic table right there. So that means if the total is 12 and protons is 6, that means you got to have 6 neutrons also. So it also has 6 neutrons. That's called carbon-12. The one I just did right there was carbon-13. And again, that's got 13 protons plus neutrons, so 6 protons, right? The protons doesn't change for an element. It's got to be the number in the periodic table. And then that works out to 7 neutrons. But those are not the only 2 that are found. There's one more found in nature. There's very little of it, but it's developed in the atmosphere, the upper atmosphere of the Earth. Essentially, solar radiation and interstellar radiation is constantly striking the Earth's atmosphere, and it will cause a reaction, a nuclear reaction, to form this thing called carbon-14, which has 14 protons and neutrons. So 6 protons, again, that's not going to change. So 14 minus 6 is 8. So you get 8 neutrons. And there's even one more. And this one is used this does not occur naturally. This is generated in laboratories, medical laboratories in particular, to do what are called PET scans. So proton emission tomography is carbon-11. So it's got 11 protons and neutrons. So 6 protons. So 11 minus 6 is 5. So it's only got 5. This one's unstable. It essentially breaks up into other atoms within 24 hours. So it's really unstable. This one breaks up. This one's also unstable, but it's more stable than carbon-11. It will last a few thousand years on average, 5,000 years on average, 5,000 to 6,000. These 2 are stable. They last, as far as we know, billions of years. Okay, so those are all examples of isotopes. So if you ask yourself, hey, what's an isotope? An isotope is a particular form of an element. It's a form of an element. So carbon-12 is an isotope of carbon. It is the isotope which has 6 neutrons. Carbon-13 is a different isotope of carbon. It is the isotope that has 7 neutrons. Carbon-14 is an isotope of carbon. It is the isotope that has 8 neutrons, okay? So as you go through those problems, keep that in mind, that you can have different isotopes for each element. And pretty much all, maybe 1 or 2 exceptions, all elements have different forms. They just have different numbers of neutrons. And the whole discussion of the number of neutrons is just a topic beyond the scope of this course. That's something you would talk about in a more advanced course. Okay, so let me show you then our kind of next issue to deal with, which is the periodic table. Okay, so this is section 2.4. And it's a discussion of the periodic table. Pretty easy stuff, quite frankly. It's just sort of studying the table and finding stuff in there to think about. So let's remind ourselves, the way this works is you've got an element symbol, typically. So let me pick one that's not carbon. Let's pick nitrogen, I guess. Nitrogen, element number 7, and then it's got this number down here. This number down here is called the atomic mass, and we'll talk more about the atomic mass later. This one right here is the atomic number. So be careful of the terminology, right? You've got atomic number, which is the number of protons in one atom of that element. The atomic mass is the mass of one atom. We'll talk about that later, of that element. And then you also have the mass number. The mass number is not the same as the atomic mass. They're related to each other, but they're not the same. The mass number is the number of protons and the number of neutrons. Okay, so let's take a look at an example here. Essentially, in this type of problem, what they want you to do is they want you to just kind of fill in the missing information. So this is all about names and symbols of important elements. So they're picking some important elements. Okay, that's a little bit subjective, which ones are important. But the first one is potassium, so they give you the name. And then they just want you to give the symbol. Okay, now the symbol is going to have either 1 letter or 2. And then the next one, they don't give you the name, but they give you the symbol. Okay, and then the third one, they give you the name, but you got to look up the symbol. Couple where they give you the symbols, and you got to write the name. And then the last one's chromium. Okay, there we go. Okay, so all you got to do is just look at your periodic table, find one that has the names and not just the symbols. These days, most of them have both. Okay, so there's roughly speaking 118 elements. If you look at this, there's the heaviest one, or the most complex one, element 118, OG, okay? And then it starts all the way, oops, sorry, I didn't share screen. Let me share screen. There we go. So element 1 is all the way up here. That's hydrogen. Okay. And then the heaviest one, as I was saying, is all the way down over here, element 118, which is OG. Okay. Generally, we're not that concerned with these elements all the way down here. If you're building atomic bombs, then you might be interested in stuff down here. Or if you're doing, advanced work in semiconductor research, you might be interested in these ones down here. So most people that come into chemistry are either biology majors or going into medical field. So the elements you're mostly concerned with under those circumstances are really around the first 30. I mean, there's a few more beyond that one. So you might be, you're interested in 35, which is bromine maybe a little bit. But really the first 30, in terms of biology, in terms of evolution on Earth, the first 30 are really the important ones. But again, not completely. There's some that are important. If you're going into engineering, you might be interested in some that are a little further down in terms of metals, for example, silver and zirconium. Those are metals that are used in society, so they're important as well. Okay. So all you got to do is look these things up and, just kind of be careful. Cr is chromium, whereas Co is cobalt. Most of them are using what we might consider English words, like cobalt is Co, manganese is Mn, but a few of them use the old Latin words, right? So some of these elements have been known, probably since before there was an English language. So iron is not Ir, iridium is Ir. Iron is Fe for ferrum, right? And sodium, for example, is not So, it's Na for natrium, right? So if you're doing Alex, just be careful. Don't put in the Latin name. Don't call it ferrum and don't call it natrium. Call it iron and call it sodium. And here's potassium, right? So these are elements that have been known a long time. Lithium hasn't been known that long, right? So that's why that one's in English, essentially. Okay. So there we go. So let me just come back up and we'll look at that problem. Oops. Okay. All right. So let's take a look at it again. Sorry, I just erased everything. It's one of the little glitches of Zoom. Okay, so let's do potassium. Now I'm gonna, just to kind of add a little bit more to it, the Alex problem doesn't ask you to do this, but I'm gonna do it anyways. I'm gonna write the symbol next to it. Okay, so here's your symbol. And then I'm gonna write the atomic number next to it, just to give yourself some practice. So when you look up potassium, that's element number 19. Okay, so there's the name, the symbol, the atomic number. We don't know the mass number because the mass number is specific to an isotope. So they would have to tell us potassium 20 or potassium 18, and then we would know the mass number. But you do know the atomic number from the periodic table. Okay, the next one is calcium. So they tell us it's calcium. I'm sorry, they give us a symbol. So Ca is calcium. And that's element number 20. So notice calcium is right next to potassium. Presumably in the Earth's crust and in the oceans, the lighter elements are relatively in high concentrations. So there's a lot of calcium, there's a lot of potassium on the Earth. There's fewer, as you go down the table, there's fewer and fewer elements. So if you get down to element number 80, which is mercury, there's much less mercury in the Earth than there is, say, calcium or potassium. So life uses, the more readily available elements for biological processes. So potassium and calcium are pretty high up. So they're, pretty prevalent in bones, for example, right? So the next one is oxygen. They give you the name. Okay, so there's oxygen. You look that one up, and that is O for oxygen, and that has an atomic number of 8. So 8 protons in one nucleus of oxygen. Next one is Br. Okay, Br, you look that one up, that's bromine. And that's element number 35. 35 protons. So that's, that's relatively heavy. There's not much bromine in our bodies. There's certainly much more chlorine. Chloride is a very important ion in metabolic processes. Bromide, not so much. There's not that much in our bodies. It's heavier, so it's a lot more protons. Next one is Mg. Okay, now this is one that you can be careful about because there's Mn, which is manganese, and then there's Mg, which is magnesium. Magnesium is Mg. Magnesium is, let's see, that's rendezvous, so that must be, gosh, is that 38? I guess that's element number 38. Calcium, oh no, magnesium, sorry, magnesium's above calcium. It's number 12. Okay, magnesium is 12. And then you have chromium. They give you the name chromium. Again, be careful with the C's. You got C for carbon, you got Cr for chromium, you got Cu for copper, you got Co for cobalt. There's a lot to start with C. And then chromium is number 24. That's element number 24. Okay. So there you go. So that's just kind of looking at the table, filling them in. As you go through the ALEX problems, you can practice those. And I just put in the atomic number just to give you a little bit more practice in terms of thinking about that. Okay. The next issue is they have these questions. So this one's called reading a periodic table entry. Okay, so reading a periodic table entry. And what they do is they say they want you to write every symbol. So write the symbol for every chemical element with an atomic number greater than 50, so more than 50, so not including 50, greater than 50, and atomic mass less than 136.5 U. Okay, so let's talk about this one here. This is the first example where they're introducing this idea of the atomic mass. So let me talk a little bit about atomic mass. Atomic mass is an important aspect of our elements. Okay, that's the atomic mass down there. This up here is the atomic number. The atomic number is the number of protons. So it's not a mass, it's just counting how many of these little particles are in one atom. So every carbon atom has 6 protons. The atomic mass is a measure of the weight. Now, technically, it's not weight, we call it mass. So let me put it weight in parentheses of an atom of this element. Okay, so it's how much one atom of that element weighs. Now, it's a little bit complicated, and we'll talk about it probably next week. But that number is shown down at the bottom. It's essentially how much it weighs, okay? So what they want us to do is they just want us to look through the periodic table and just look for every element that has an atomic number greater than 50. Now remember, the periodic table goes up to an atomic number of 118, right? So that in theory could be 68 elements. That'd be a lot to write out. But they limit it. They say, look, don't go beyond an atomic mass of 136.5. So once you get up to 136.5, stop. So what happens is this is going to get to 136.5 before you get up to too far up. So they're not going to have you write 100 elements or 68 elements. They're going to have you write a few. Okay. So you're taking into account both numbers. So let's take a look. What I'm gonna do, instead of sharing the screen of the periodic table, I'm just gonna go ahead and write these down. So I'm gonna start at, this is what I'll do. I'll start at element number 50. We're not gonna include 50 because we wanna go beyond 50, but I'll start at 50. So 50 is SN, and it has an atomic mass of 118.7. Okay. So then the next element over is element 51. And element number 51 is antimony, which is SB, right? So there's one of those Latin elements, and it's 121.7. And then the next one over is 52. And 52 is technetium. I'm sorry, tellurium. My apologies, tellurium. And tellurium is 127.8. Next one over, 53. 53 is iodine. That is actually one that's important in biology. And then the next one over is xenon, which is 54. And xenon is 131.3. Okay, so now we're going to start, but we haven't quite gotten there, right? We've gone up to 54. We still have to go one more. So I'm going to come over here and do element number 55. Element number 55 is cesium, and it's 152.8. And so we're getting pretty close, right? Oh, actually, I'm sorry, it can't be 152.8. It's 132.8, sorry. There we go. So it looks like we're getting pretty close. We're almost up to 136. So let's go to the next one, 56, which is barium. And barium is 137.3. Okay, it looks like we're done, right? So we just need to have an atomic number greater than 50. So we're not going to include 50, greater than 50. So that would include 51, 52, 53, 54. But we want to have an atomic mass less than 136. So we would also include 55, but we would not include 56, right? Because that's greater than 136.5. So we're not going to include those two there, okay? So all we have to do is just write the symbols. So we don't have to go write everything that's down here in the periodic table. So all we got to do is just write, hey, antimony, I'll use a comma, tellurium, iodine, xenon, and then cesium, and that would be our answer, okay? So we're just writing the symbols. So what's kind of useful about that particular problem is that it's getting you to think about two numbers, right? The first number is the atomic number, the number of protons. It turns out the number of protons determines what element you have. So if something is 6 protons, that means it's carbon. But the atomic mass is how much that weighs. How much does this particular element weigh? And we'll talk more about atomic mass as we move along, okay? So that one's a interesting little example. Okay, let's talk a little bit about periods and groups. So periods and groups work this way. Periods are this way, horizontal. They go horizontally. And then groups go vertically down, right? So a period is all the elements in a row. Think of it as a row, and then think of a group as a column. Okay. Now, there are different systems for periods and group, or I should say there's different systems for periods. It gets updated every once in a while, every 40 or 50 years. So the way it works is if you have, let's try, for example, this first group. Sorry, NaKRBCSFR. Okay, so that's the one, it's on the far left, right? Hydrogen's on the far left. This is number 3. This is number 11, 19, 37, 57 minus 2 is 55. And then I think this is 80, right? So it's, yeah, it's 87. There we go. Okay. Trying to figure, we're doing this from memory, okay? So those are the atomic numbers. So that's the first column. I generally call them columns, but the technical name is a group, right? So that's the first group. The first group, there's 2 very common numbering systems. So the first system is the older one, where you just say, hey, which one's in it? It's in the first column, so it's column 1. And then you put an A next to it. And A essentially means it's a main group element. It's not what we call a transition metal, okay? The more modern system is you just put the number of the column it's in. It's in the first column, so it's column number 1, okay? So it's in the first column, it's in group 1 or group 1A. So you just have to figure out which system Alex is using. Alex is using the system where you put the letter A, okay? So if you're Googling a periodic table and you're trying to figure out which column it's in, you might want to look at the ones that have the letters, the A's and the B's, okay? So the first column is 1A, the second column is 2A. So there is, there's nothing actually right next to hydrogen there, so you have to go down to beryllium. So beryllium is right here. So this is 2A. Okay, so underneath beryllium is magnesium, calcium, strontium, barium, and then radium. So when you get down to this last row down here, francium and radium, all those elements are radioactive. They're just they're unstable, but the ones above are pretty stable, okay? So this would be group 2A. And then what happens is then you get these elements which are called the transition metals. So starting right here, you have scandium, it's right next to calcium. You have scandium and then yttrium, I'm gonna write that like that, lanthanum, and then actinium. So this one, it starts with the number 3, but it then has a B next to it. So just be careful. The Alex system they're using is the American system, and the American system is an older system, and we use the letter A's and B's, okay? So the group is, would be 1A, okay? Now the period system is easier. The period system is just what row it's in. So period, you don't even have to worry. Just look at what row it's in. Okay, so if it's in the first row, it's in period 1. If it's in the second row, it's in period 2. It doesn't matter where it is in that row, right? So just remember, period is row and then group is column. So, all of these elements here, the next one's titanium. These ones are going to have B's. And it's going to go all the way to the end when you get to 2B. See, it goes backwards then. And it goes down to 1B and 2B. And you have zinc. Okay. So all these ones in the middle are B's. And that just has to do with their chemistry. It's an older system really for chemists to kind of think about their chemical behavior. So what happens is, the elements that are in 3B behave similarly chemically, And then the elements that are in 2B, like zinc, cadmium, and mercury, they behave similarly. So they're called 2B. And we don't need to go into the details of that. The point I want to make is then when you come over here to boron, it now goes back to the A's. So now it's 3A, carbon is 4A, nitrogen is 5A, oxygen is 6A, fluorine is 7A, and then neon is 8A. Okay, so it goes 1A, 2A, skip all the B's, then 3A, 4A, 5A, 6A, 7A, and then finally 8A. Okay, so it can be a little bit confusing, the system, but the advantage of this is you don't have to memorize it. All you need is just to get yourself a copy of the periodic table, and you'll be set. Okay. Okay, let's plug this iPad in. Okay, so one type of question they'll ask you in that is they'll just say, hey, in what period is lithium in what group is lithium in? Okay, very simple. They're just going to ask you what period, what group. That's all they're doing. It's just so that you know the difference between a period and a group. And remember, think of the period as being the row. That's your period. And those are very simple. It just goes 1, 2, 3, 4, 5, 6, 7. So hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, right? Okay, so lithium is in the second row. So that would mean that it's in period 2. Okay, in what group is it? Remember, the group is vertical. So what column? Okay, so lithium is in the first column. Okay, so it's in column 1A or group 1A. And so there would be your answers. So it's 1A. So it's in period 2 in group 1A. The significance of the group is that the elements that are in the same group, not the same period, but the same group, so the same column, they have similarities in their properties. And a good example of that is lithium and sodium. Sodium is an important nutrient, right? It's essential for cell function. It's essential for muscle function and the entire nervous system. We can't exist without sodium. Can't survive without sodium. Lithium, on the other hand, is not, as far as we know, it's not at all essential.
Oh.
Not required.
Well,
However, it does behave chemically similar to sodium. So if you ingest lithium, the body will try to treat it as sodium. It will behave very similar to sodium, but there's some slight differences. It's a little smaller than sodium, and being a little bit smaller, it has a little more electrical charge per volume unit. So if you have the same amount of electrical charge, but it's smaller, that's a little more dense electrical charge. It's a little different. And so it actually affects the central nervous system. So it can be used as, it's one of the first mood altering drugs used by the pharmaceutical industry. It's used even today, it's used for bipolar disorder because it behaves similarly to sodium, but a little bit different, okay? So that's sort of the introductory problem of the periodic table. Now let's take a look And let's see, using the periodic table to identify similar elements. Okay. So using the periodic table, to identify similar elements.
Oh. Oh.
So what they're going to give you is they're going to give you an element. So in this case, it's nitrogen. And then they're going to give you several elements. And they're going to ask you to pick which one is the most similar to that particular element. So which one is most similar to nitrogen? And that is purely based on the position in the periodic table. Think vertical. Oh, let me write this a little bit further down here, sorry. So most similar is that they're going to be in the same family, which is the same column. All right, so think vertically, up and down. If they're in the same column, they're going to behave very similarly. So what you do is you say, okay, you got nitrogen. So which of these elements is in the same column as nitrogen? So nitrogen's element number 7. And so just kind of comparing these, strontium's all the way, so this is in group 7A, all right? Strontium is all the way over in group 2A. It's element number 3. It's not even close, right? Strontium is nowhere near nitrogen. Okay, they're in completely different column. 2A versus 7A. I'm sorry, 5A. My mistake. 5A. 2A and 5A are not that close to each other. Next one is iodine. Well, iodine is in 7A. It's way down over here, right? So, no chance. 5A, 7A is not the same. Next one is fluorine. Okay, well that's, fluorine is here, so it's in the same row as nitrogen, but it's in a different column. And the point here is that the row doesn't tell you. If they're in the same row, that doesn't mean they're going to behave similarly. What's going to make them behave similarly is in the same column, the same family. That's what we call them family, right? Family, they're going to be the same. Okay. So the last option here is they give you phosphorus, and phosphorus is right below nitrogen. It's element number 15. So there's your answer. Phosphorus is the one that's going to behave most similarly to nitrogen because it's in the same family. It's in the same column. Okay. So right there would be phosphorus. And then the next thing they do is they want you to find the one that's least similar to, and let's take a look at the example here. Here they're doing nitrogen. Okay, so here's what I want to point out about that. In general, it's useful to think of the periodic table as having 3 different regions. There's really kind of 4, but 3 is probably the way to do it. So you first have 2 families here, 1A and 2A, okay? These elements here are going to behave relatively similar to each other. The first family, those elements are similar. So you got hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Okay, so there's one family. Second column is beryllium, magnesium, calcium, strontium, barium. Okay, those elements are 1A and 2A are going to behave very similar to each other. Okay, then you've got these elements in the middle, and these are called the transition metals. Okay, and these are going to behave similar to each other. Okay, so these groups are called the main group metals. So there's your main group metals. Then you got your transition metals. Now, if you see those two rows, they sometimes break out down here. These ones behave very similar to the transition metals also. They're called rare earth metals or lanthanides and actinides, but chemically they're similar to transition metals. Then over here, you've got what are called nonmetals. And so those are the ones like the helium. So this is, group 3A, 4A, 5A, 6A, and then 7A, and then 8A, sorry. So you've got helium, neon, argon, krypton, xenon, radon, okay? But you've also got these other nonmetals. So what you want to do is this, for least similar, okay? Most similar is easy. It's just got to be in the same column. The one that's in the same column is going to be the most similar. So least similar would be further away in the position in the table, okay? So if we're comparing nitrogen, and let me erase that and just write it over here. So nitrogen is over here. And then we got phosphorus. And then our choices were strontium, which is all the way over here. Iodine, which was right here. And fluorine, right? Fluorine was right here. Here's what you want to do. If they're saying which one is the least similar, metals are least similar to nonmetals. They behave very differently. So if you have a metal over here and you're comparing it to a nonmetal over here, what I'm claiming is the nonmetals behave more like each other than they behave like the metals. And the metals behave more like each other than they do behave like the nonmetals. So if you're comparing nitrogen to either iodine, phosphorus, or fluorine or strontium, the one that's going to be the most different to nitrogen would be the metal. They just behave very differently. So for most similar, it's easy. Just make sure they're in the same column, right? Like these two. For least similar, the element, take the one you're looking at and look for the element they give you that's on the other side of the periodic table. Okay, so strontium's all the way over here. That's going to be very different from all of these nonmetals. All the nonmetals behave more like each other than they behave like metals. Okay, kind of an interesting question, but a good one. Okay. And the last topic that they have you do in this section of the periodic table is looking at the difference. So you're going to distinguish a metal from a nonmetal by physical properties. Okay, so these are sort of little word problems. Okay, so let me do this. The metals, again, the metals are these first two columns here, 1A and 2A. And these are called the main group elements and the main group metals. Then you got these elements over here, which are the transition metals. So that's, 3B, 4B, 5B, 6B, and then it comes back and it goes 1B and 2B. And then over here, you got the nonmetals. Well, actually, let me be a little bit more careful about that. You've got what are called the metalloids. Let me write And then you got the nonmetals. Okay, so these are the 3A, 4A. A, 6A, 7A, and then 8A. Okay, so here's the difference. So these are metals here, and these are metals here. Those are both metals. So metals, they conduct electricity. They're very good conductors of electricity. They conduct heat very well. They're good heat conductors. Okay, so we can cook with them. They also are what we call ductile. Okay. Now, ductile means that if you try to pull on both opposite sides, they actually kind of like taffy. You can pull them out into wires. That's ductile, ductility. Okay, you can pull them into wires. And then they're malleable. Malleable means that you can pound on them and they don't break. Okay, so if you take a penny and you put it on a train track, you take a coin, you put it on a train track, the train runs over, it doesn't break it into pieces, it doesn't crumble, it actually just gets flattened out. That's malleable, right? You use a hammer to pound stuff. The head of the nail will spread out a little bit, but it won't break into little pieces, okay? The nonmetals are the opposite. The nonmetals do not conduct electricity very well, so we don't make wires out of nitrogen. They don't conduct heat, so we don't make cooking pans out of oxygen. They are not ductile. If you pound on them, they tend to break, or they're gases to begin with. And they're not malleable, okay? So you can't do that. You can't pull on them or break or pound on them. So let me show you, I'm gonna stop share here. And I'm gonna just kind of look at this problem here for you.
Professor, sorry, could you quickly go back to that thing that you wrote?
Probably not. What did I write?
You know, you were just writing, you know, conducts electricity, conduct that, like that very last page.
I'll tell you what, after we do this problem, I'll write it again. It's very simple. I'll try to write it more neatly too. Okay, so let me show you an example here. It says here in the table below, there are descriptions of the experiment on samples of 3 different elements. There's 3 different elements. Decide whether the element's a metal or a non-metal if you can. If there's not enough info, don't, okay? So there's 4 things. One is, do they conduct electricity? That's a metal. Do they conduct heat? That's a metal. Are they ductile, which means if you pull on them like taffy, they stretch without breaking. That's ductile. And then the 4th one is if you pound on them, does it crumble? And that's malleability. So metals conduct heat, they conduct electricity, they're ductile, so you can make wires, and they're malleable, so you can pound on them. Okay, those are the 4. Non-metals, none of those. They don't have any of those properties. So let's see. Element 1 is a moderately soft, silvery gray solid. A 5 centimeter by 5 centimeter square of it is only 1 millimeter thick. It's heated with a flame at one end. Where the flame touches the square, the sample rapidly turns red and starts to melt, but the rest of the square remains cool to the touch. Okay, now that's interesting. That's a little tricky. So let's take a look at what they're telling us. They're telling us it's a solid. So metals are solids at room temperature. Some nonmetals are, though, as well. So that doesn't exactly tell us, but it's evidence it could be a metal. It's heated with a flame at one end. Where the flame touches the square, it turns red and starts to melt, but the rest of it remains cool. Okay, so there's an issue of heating, right? Imagine a pan. If you're heating a pan and you heat it at one end, the other end will turn hot very quickly because metals conduct heat very, very well. So the fact that it's telling us it's melting on one end and it's not even hot on the other end, that tells us it cannot be a metal, right? Metals conduct heat. So the second one looks like it's a nonmetal. I mean, the first one looks like it's a nonmetal, just based on heating. Now let's look at element 2. Element 2 is shiny. Shiny usually means metals, but again, there are some elements that are shiny that are nonmetals, like carbon can be. Silicon can be shiny. Element 2 is shiny, solid, so it could be a metal. 5 centimeter by 5 centimeter square of it, only 1 millimeter thick. It's flexed and it snaps in half. Now that's the key right there. That's really the issue of ductility. If you're bending, if something bends, that's sort of ductility, or it's related to ductility and malleability, right? I guess that's more malleability. Malleability is whether it can change its shape without breaking. So the fact that it snaps in half, that's pretty good evidence that it's a nonmetal. It's certainly not a metal. Okay, metals generally don't do that. If you do it forever, right? You can take a paper clip. If you do it enough, eventually it will snap. But if you just do it once, a paper clip is not going to snap. So it's not a metal, could be a nonmetal. Element 3, hard silvery gray solid, 10 grams, that's mass, 10-gram cube of it is put on a hot plate. And eventually, after 1 minute, the temperature of the top of the cube has risen by 50 degrees Celsius. So you're putting it on a hot plate. Oh, the top of it after a minute has risen by 50 degrees Celsius. So that means it got hot at the top. So the tricky thing about that is they say after a minute, right? So, if you have a nonmetal, it could get hotter too. It doesn't mean like it's not going to conduct heat. So that one's hard to say. I would say you can't decide. It could be a metal because it got hotter at the top. But since they took a whole minute to do it, that's a long time. So even a nonmetal might conduct heat that well that after a minute, if it said after a second, then I would say it's most likely a metal. But after a minute, it could be either. So you probably can't decide with that one. Okay. So let me do as Tosca requested, which is to write that down for you. Which is the metal. So let me write it this way. The metal conducts heat well. In fact, let me write it this way. It conducts it quickly. So that third one, the issue is quickly, right? A minute is a long time to heat something. So the fact that it got hotter after a minute doesn't really tell you much. If you said a second or 2 seconds, then that would tell you it's most likely a metal. Okay, so conducts heat quickly, conducts electricity well. Metals are very good electrical conductors. Okay. Third one, ductility. It's ductile, which means you can stretch it. It stretches like taffy. Okay, and then the last one is malleable, which means it's bendable and also it flattens. All right, like a penny. Okay, so those are the 4 properties. The nonmetals, they can conduct, everything conducts heat a little bit, right? So they can conduct heat, but they conduct heat very slowly. Slow heat conduction. And again, that's why that last one was hard to tell. That's why you probably just can't tell. They don't conduct electricity. So we don't make wires. I mean, we don't make wires out of nonmetals because they don't conduct electricity, but also because they're non-ductile. They break, and then these ones are non-ductile. So they break, and they're non-malleable. So that means they if you smash on them, if you hit them with a hammer, they crack, crumble, they break. Okay. Now, some nonmetals are gases at room temperature. Not all, but some of them are. Some of them are nonmetals, so those ones are easy, right? If it's a gas, it's room temperature. So the noble gases. These are called the noble gases. They're all gases at room temperature. Okay, so those are nonmetals. But other elements are nonmetals as well. So for example, fluorine is a nonmetal. Okay, that one right there is a nonmetal. Oxygen is a nonmetal. Nitrogen is a nonmetal. I mean, they're all nonmetals, but they're all gases at room temperature. Okay, so gases are nonmetal. I mean, if they're gases, they're nonmetals. But some of the nonmetals are solids. So that's why that in that particular problem, they're getting at the issue of, hey, it could be a solid, but it might be a nonmetal. And so, for example, carbon. Carbon is a solid, but it's not a metal. It doesn't conduct electricity very well. It conducts a little bit, but not that well. It doesn't conduct heat all that well. So there you go. Let's see. Anything else about that one? Let me just see if I can look at another one, if anything's any different. Okay. So yeah, so you have three choices. It's either a metal, it's a non-metal, or you can't decide. If it doesn't conduct heat or electricity very well or very slowly, then that's a non-metal. But sometimes you just can't tell. That last one, you just really couldn't tell. Okay. All right. So that was a pretty lengthy discussion of the periodic table. There's more that we could say about it, but I did want to go through a bunch of those problems just to kind of give you an idea of how to use the periodic table. Next week, what we'll do is we'll look at the atomic mass scale. And so I talked a bit about it today, this idea of the atomic mass, right? We're going to talk about it next week. We're going to go into that. We're going to go into calculating it and looking at scales and such like that. So we'll probably look at section 2.5 next week. And so those are calculations, by the way. And if we have time, we'll get a little bit into section 2.6, which is ions. Those are cool. Ions are cool. That's real chemistry. And ions and ionic compounds are important for anybody that's a biology major, because when you talk about the physiology of the body, ions are where it's at, right? Sodium ions, potassium ions, calcium ions, chloride ions, those are all important, phosphate ions when it comes to physiology. Okay, so have a great week. I'll post this if you want to watch it, and reach out to me if you have any questions this week. Take care.